this is the fifth experiment of digital design where we explain two runs. One is 7-segment decoder. How does it work? What does it exactly mean? And then BCD adding. So 7-segment decoder is actually an FND 505. It looks something like the normal stop signs or LED lights all together. I mean combination of that. It looks something like that. Where these places are the lights, and on particular combination of the input, these lights glow, and so we have a particular number displayed. So the idea is that we have a counter that will give an output in the form of a number. That number will be used, the number will be from 1 to 15. So a particular combination of that number will be, let's say if it is 9, so 1001. 1001 will be converted into 7 segments, and those 7 segments will be used to generate a proper number. See, this is from A, B, C, D, E, F, G. So if I want to display 0, that means everything should glow except G. So the logic says that if 0 has to be displayed, that is if the output from the counter to the 7447 is 0000, or if the initial table says it's 0000, then my A, B, C, D, E, F, G should display 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 6, 0. So this is the logic for 0000. If it is 1, 1, 1, 1, so that makes it 15. 15 cannot be displayed on FND, so just consider it from 1 to 9. If 9 has to be displayed, then for 9 to be displayed, E should not come. So instead of E, everything should glow. So you should have 1, 2, 1, 1, 1, sorry. 1, 1, 1, 1, 0, 1, 1. This is how the functions. Similarly, we have 0 ones for different combinations. So this is actually the function for A, and similarly there is function for B, C, and till G. So using these functions, you can implement, or it is already being implemented in 7447. It is 74 standing for counter, standing for timer, and 47 means that it is converting from 4 input to 7 output. And the logic for that is given. If you have any function, then how the function implementation works. In similar manner, you have to implement all these functions. This is already done internally in 7447. So basically, I have a counter. Counter gives me a number. This number is converted into 7 bits or 7 digits using these logics, and those 7 bits are used to light an FND. This is how 7-segment decoder will work. So main things will be involved in this is connection of this circuit, giving A to KTL logic. KTL logic will generate this pulses. Negative is triggered because there is a bubble over there, and then when 7493 is created, I mean the numbers are created, whatever is there, then correspondingly the FND will go accordingly. So the idea is that if initially the TTL is stating 0001, then 1 will go over there, so B and C will be on. So if it is 2, I mean on the next clock pulse, then 2 will be on, or the corresponding number that will glow is 2. If it is 3, that is the third clock pulse, then 3 will be on, or 3 will be displayed on the FND, and it will keep moving. One more thing about this is, because this can only display till 9, so after 9, that is from 10 to 15, the numbers that are displayed over there are very big. I mean 10 can be this or any different symbol. So that is why we mostly consider or change it from a binary number to a BCD number first, so that any number that comes as an input to an FND is always between 1 and 9, so that 0 and 9, so that it can be displayed properly. So that will be done in BCD adder. Okay, so this is the next part of the experiment, that is BCD adder. We first of all discuss about what exactly is BCD addition. BCD addition means that when I add two numbers, they cannot exceed, the addition cannot exceed 9. So what do we do exactly for that? We'll discuss about that, and that involves the logic that is there behind the BCD added circuit that has been given over here. Okay, so first of all, BCD addition involves, if I have any number, suppose I am adding 7 and 8, 7 and or say 7 and 10. 7 and 10 gives me 7 and 8. Say 7 and 8 gives me 15. So 7 is actually 0 triple 1 and 8 is 1 triple 0. Adding them means they can be added using 7 4 8 3, but adding them should give me 15. 15 is triple 4 times 1. This number is greater than 9. Once any number is greater than 9, then 6 is added to it. If we add 6, that is, we add 0, 1, 1, 0. 0, 1, 1, 0 will give me 1, 0, carry 1, 1, 0, 1, carry 1, 0, carry 1. So, finally, I am left with this is 5 and 1 as an additional carry. I started with 8 and 7. 8 plus 7 is 15. I am left with 1 carry and 5 in decimal. So I have 15. So this is how BCD addition works. And the idea behind adding 6 is genuine. So we add 6 every time in order to convert any number which is not in BCD to BCD. So we have a number, two numbers are added, we get a sum. We see the logic, if it is greater than 9, then add 6, and then add the sum and 6 to it. See, two numbers were initially added, the sum was checked. If it is greater than 9, then add 6 to it, find the answer and display. Logic is add two numbers, see if the sum is greater than 9. If it is greater than 9, add 6 to it, otherwise leave it as it is and then display it. Alright. So let's see for the logic. The truth table for any number that will be greater than 9 is, suppose 9 is 1001. So if let's say the sum gives me 9 or any number greater than 9. So 1010 will be greater than 9, 1011 will be greater than 9, 1100, 1101, 1110 and 1111. These are the sequences that will happen after 9 or 9 or after 9. So what is the scenario over here? Let's say this is S3, S2, S1 and S0. Okay, so we can say, just have a look, leave 9. In these two cases, S1 and S3 are 1, and in these remaining cases, S3 and S2 are 1. So I can say that when S3 and S1 become simultaneously 1, then I have a number greater than 9. I can also say that if S2 and S3 simultaneously become 1, then I have a number greater than 9. Okay, and apart from that, you also know that when you add two numbers using 7483, then addition gives me a carry. A carry received in addition of two numbers automatically means that the number was greater than 1111, 15. So it's obviously greater than 9. So the logic can state that if I have a carry in my initial sum, or I have these two numbers greater than 1, equal to 1. I mean S3 and S1 are equal to 1, or I have S3 and S2 equal to 1. In all the three cases, either of them, if they are 1, then I should have a number greater than 9. Now, if the number is greater than 9, then obviously 6 has to be added to it. To add 6, what do we do? We have 6 means 0, 1, 1, 0. So that means ground these two and make these equal to 1. Right? They have to be grounded and these have to be made equal to 1. So see the logic. Two numbers added, you get the sum S3, S1. If S3 and S2 say S3 and S2 combined and if they are equal to 1 or S3 and S1 are equal to 1 or the carry is equal to 1. We used 2 input OR, so that's why 2 ORs, otherwise 3 input OR can be guaranteed for all the 3. So if any one of them exists, then I have 1 coming out. If 1 comes out, then what do you do? Make this ground and make these two 1. So this will give me 6. So 6 is one of the inputs that have to be added. We had to add 6. Now once 6 is added to the remaining whatever is left from coming out from the initial sum. 6 is added to it. Now this final addition gives me an output. So that output can either have a carry or not have a carry. If it has a carry, if any one of these has a carry, this will come as the MSB or the most significant digit to denote that it was 15. Our case was 15, right? This was 15. So to denote it was 15, this will be turned on. And the remaining part or the remaining digits will come out into 7447 as an in RAM 1. We will have 4 inputs converted to 7 outputs and displayed on FAT. So 1, 5 and 5 on this will indicate that it was 15 when 7 and 8 were given as inputs. So this is how BCD adder works.